Welcome to AI Peer Review. Today we're diving into a really interesting paper proposing a new take on language image pre-training.
Yeah, it's called Sigmoid loss for language image pre-training.
Yeah.
And it puts forward this uh, pairwise sigmoid loss, basically an alternative to the usual softmax contrastive learning we see a lot.
Right, the standard approach. So, given your background, this seems like a great chance to really get into the weeds on these loss functions in multimodal learning.
Absolutely. Let's unpack it.
Okay, so starting point. What's the problem with the standard softmax loss? Why look for an alternative?
Well, the standard softmax contrastive loss, it fundamentally needs let's say, a global perspective. It has to look at all the image-text similarity scores within a batch to normalize things properly.
Okay, so every pair's loss depends on every other pair in that specific batch.
Exactly. And that's where issues can creep in. For one, just implementing it naively can lead to numerical instability. You often need tricks, like subtracting the max value, just to keep the numbers stable.
I see. And beyond stability.
The bigger thing, maybe, is how it tightly couples the batch size to the loss itself.
Mm.
Your loss calculation intrinsically depends on how big your batch is.
Right. Which I imagine complicates things when you're trying to scale up or train across many machines, or even if you just have memory constraints.
Precisely. It limits flexibility.
So this paper brings in sigmoid loss, or siglip, they call it. How does it break away from that batch dependency?
It's fundamentally simpler in its view. It looks at each image-text pair completely independently.
Independently. Okay, how?
Instead of that global comparison and normalization, it treats it as a bunch of separate binary classification tasks. Is this specific image-text pair a real match? Yes or no? Positive label for a match, negative for all the others related to that image or text.
Ah, okay. So it's just predicting match or no match for every single potential pairing.
Pretty much. Algorithm 1 in the paper lays out the pseudocode. It's quite clear.
Can you walk us through the key steps there?
Sure. First, you normalize the embeddings, both image and text. Standard L2 normalization, so the dot product later gives you cosine similarity.
Makes sense. Get them on the same scale.
Right. Then you compute the dot product. But crucially, you scale that dot product by a learnable temperature parameter, and you add a learnable bias term.
A bias term too. Okay.
Yeah, we'll probably circle back to why that bias is important later. But after the scaling and bias, you apply the sigmoid function. And the target label is simple. +1 if it's a true pair, -1 if it's not.
Got it. So operating pair by pair avoids those batch-wide operations. What does that mean for efficiency?
Big gains, potentially, because you don't need those big collective operations across the whole global batch to calculate the loss for each pair. Distributed training becomes much simpler.
Less communication overhead between devices.
Exactly. Each machine can kind of chew on its local pairs more independently before needing to sync up as much. The paper argues this really helps, especially with smaller batch sizes where softmax can be a bit shaky because the normalization term is less reliable.
Okay, and memory. That's always a big one.
Sigmoid tends to be lighter on memory too. Figure 1 in the paper has a nice diagram showing how they do it efficiently in distributed training with a chunked approach.
Chunked.
Yeah, instead of needing the whole similarity matrix for the entire global batch, which is size b squared, they only need the similarities for the pairs on each device, which is size b squared, where b is the local batch size.
Ah, so it avoids needing all devices to gather all the embeddings from all other devices, that expensive all-gather operation.
Precisely. That's a major bottleneck usually. Avoiding that means you can potentially push to larger effective batch sizes with the same hardware, or just use less memory overall.
Okay, makes sense. Let's talk results. They introduced siglet-locked image tuning. What did they find there?
Table 1 has the numbers. Pretty impressive zero-shot ImageNet accuracy. They hit 79.8% with a B8 checkpoint and even 84.5% with a G14 model.
And this was done efficiently.
Yeah, what's striking is they achieved this with relatively few TPU-v4 chips and in just a couple of days. Suggests it's quite sample efficient.
And how does batch size play into siglet? I think figure 2 looks at this.
Right. Figure 2, the left panel, that's key. It shows sigmoid really shines compared to softmax at smaller batch sizes, say, below 16K. It's significantly better.
Which is huge for anyone not running on massive clusters.
Definitely. As the batch size gets bigger, the gap closes, and they perform similarly at very large sizes. Interestingly, they pushed Siglet up to 1 million batch size.
1 million.
Yeah, but performance seemed to top out around 32K. Just making the batch bigger and bigger didn't necessarily keep improving things indefinitely.
Interesting. So there's a sweet spot even for sigmoid. What about figure 3, looking at training duration?
Figure 3 shows that trade-off. Larger batches might seem faster initially, but they often need longer training schedules, more steps to really converge well. Smaller batches might catch up or even surpass them if the training isn't long enough for the large batches.
Got it. Now, they also have SIGLIP, where the image encoder is unlocked and trained too. How did that compare?
Table 1 again, and Figure 2, middle panel. SIGUP also showed strong results like 71.0% zero-shot ImageNet and higher. The batch size story is similar to SIGLIT. Sigmoid beats softmax below 32K.
And the peak performance.
The peak for Sigmoid came a bit earlier, around 32K batch size, and was slightly better than the softmax peak, which needed a much larger batch, around 98K, to get there.
And again, going even larger seemed to hurt both methods eventually.
Yeah, seems like there are diminishing and eventually negative returns to just throwing more batch size at the problem after a certain point.
And the memory savings from Sigmoid likely helped them even reach those large batch sizes for comparison.
Oh, absolutely. That efficiency was key to exploring that regime with the resources they had, comparing it more directly to SILIP.
Okay, what about multilingual? They tested mSigLip.
Right, Figure 2, right panel, and Table 2. They applied it across 36 languages. The interesting finding here was that, maybe surprisingly, 32K batch size seemed optimal again.
Not larger for more languages.
No, scaling beyond 32K actually hurt performance on cross-modal retrieval for mSiglip. Despite that, it set a new state-of-the-art on the XM3600 text-to-image retrieval benchmark.
So 32K seems like a recurring theme for the sweet spot with Sigmoid, even in the multilingual case.
It appears so, at least in their experiments. It suggests maybe the dynamics are different than just needing more negatives, especially with diverse language data.
They also mention using bottleneck token embeddings for mSiglib. Why was that necessary?
Just memory, really. When you have vocabulary spanning dozens of languages, the embedding table for tokens gets enormous. Using a bottleneck, basically projecting the initial token embeddings down to a smaller dimension before the main interaction, saves a ton of memory.
And it didn't hurt performance much.
Apparently not significantly, which is great. It makes large multilingual models more feasible.
Let's double down on resource efficiency. Section 4.4 mentions training SIGLIT with only 4 TPU-v4 chips. That sounds incredibly low.
It is remarkably low for this scale. And they still got really competitive results like 79.7% zero-shot ImageNet in a day and 84.5% in under 2 days with a bigger vision model. It really highlights that this approach could be viable for labs or researchers without massive compute budgets.
That's a very practical point. And Section 4.5, training SIGLIP efficiently using pre-trained weights.
Yeah, they looked at starting with pre-trained image models. The interesting trick, shown in Figure 4, was turning off weight decay specifically for the pre-trained image backbone during fine-tuning.
No weight decay on the frozen parts.
Well, not frozen, but the pre-trained backbone being fine-tuned. Disabling weight decay just for those weights significantly cut down training costs compared to standard fine-tuning or training CLIP from scratch while still achieving great performance.
Interesting optimization. Now, large batches can be unstable sometimes. How do they deal with that? Section 4.7, I think.
Right. They did see some instability, like gradient spikes, especially with very large batches. Figure 5 shows their solution: tuning the optimizer, specifically reducing the DT2 parameter in atom or eta factor.
Beta 2, the one controlling the running average of the squared gradients.
Exactly. They lowered it from the typical 0.999 down to 0.95. This seemed to calm things down, likely by making the optimizer adapt a bit faster and be less influenced by occasional noisy large gradients you might get with huge batches.
Makes sense. What about the role of negative pairs? Contrastive learning relies heavily on good negatives. Section 4.8 looks at this for Sigmoid.
Yeah, Figure 6 explores this. If they just randomly dropped negative pairs, performance went down, as you'd expect.
Okay.
But if they kept only the hardest negatives, the ones the model found most confusing performance stayed high. This really underlines that it's the informative hard negatives that drive the learning, not just the sheer number of negatives. The imbalance between positives and negatives wasn't the main issue. The quality of negatives was key.
And that learnable bias term you mentioned earlier, Section 4.9 and Table 4 revisit its importance.
Yes, they showed it provides a real benefit, especially if you initialize it to a negative value like negative 10. Table 4 has the comparison.
Negative.
The idea is it helps the model start closer to the prior expectation most pairs aren't matches. It prevents the model from outputting overly confident positive predictions early on, sort of stabilizes the initial learning phase.
Clever. And finally, robustness to noise, Section 4.10 and Figure 7.
This is a nice finding. Figure 7 suggests models trained with sigmoid laws are more robust to different kinds of noise you find in web data. noisy images, noisy text captions, even misaligned pairs within a batch.
That's definitely valuable given where most large data sets come from.
For sure, if your training data is messy, which it often is, having a loss function that's inherently a bit more robust is a plus.
They also push things further, scaling up SIGLIP and MSIGLIP in section 4.6 and table 3.
Right. They did some overtraining experiments with bigger VIT models like VITL, so 400M, and higher resolutions. As you'd expect, this pushed performance even higher, achieving state-of-the-art on ImageNet zero-shot and CoEO retrieval benchmarks.
And the scaled up multilingual models.
See their story. The larger MSIGLIP models, detailed in Table 9 and Figure 8 in the appendix, also showed really strong multilingual retrieval results. Scaling helps, as expected.
Okay, quite a comprehensive set of experiments. Let's try and synthesize this. What are the big takeaways for you from this deep dive into sigmoid loss?
I think the main story is efficiency and flexibility. The memory savings are real, and that makes larger scale training more accessible.
Right, lower barrier to entry potentially.
And the fact that it performs so well, even better than softmax at smaller batch sizes, that's a huge practical advantage for many people. You don't necessarily need those gigantic batches that CLIP often relies on.
The robustness to noise also stands out, given the reality of web-scale data.
Definitely a practical plus. And, the whole exploration around batch size limits is fascinating. Finding that performance saturation or even dip around 32K for many tasks, even with Sigmoid. It raises interesting questions about contrastive learning dynamics. Maybe just scaling batch size isn't the only answer.
Yeah, it's not just bigger is always better.
Seems not, or at least not straightforwardly.
So overall, this sigmoid loss approach feels like a significant contribution. It offers concrete benefits and could influence how we train these big multimodal models moving forward.
I agree. It shows there's still plenty of room for innovation, even in the fundamental components like the loss function. It's a constantly evolving space.
For those of you listening, particularly if you're working with large multimodal datasets or maybe face some resource constraints, Sigmoid Live seems well worth a closer look. The paper lays out the details very clearly.
Absolutely. It's a solid piece of work with compelling results.
Thinking beyond just efficiency, what strikes you as the most maybe forward-looking implication here? Where might this lead next in multimodal AI?